ever pondered over what keeps the atoms intact within a crystal structure? What stops them from disassembling? This intriguing question has its answer rooted in the concept of lattice energy, a term synonymous with the enthalpy change formation. Lattice energy is essentially a scale of the intensity of the forces that bind a crystal together. It represents the energy liberated when gaseous ions morph into a solid ionic compound, which is often referred to as lattice formation energy. On the flip side, it's the energy demanded to dismantle the ions in a solid ionic compound and transform them into gaseous ions, a concept linked to ionization energy. Consider it as the adhesive that binds the atoms within a crystal structure, or metaphorically, the electron affinity. The more potent this adhesive, the greater the energy requisite to shatter the structure, and vice versa. In the realm of chemistry, the Born-Haber cycle is our key to unravel the intricate calculations of lattice energy. This thermochemical cycle is like our compass, guiding us through the labyrinth of ionic compounds. The journey through the Born-Haber cycle commences with the creation of gaseous atoms from a solid element. This stage is powered by something called atomization energy. Subsequently, these gaseous atoms undergo ionization, another energy-consuming process, this time involving ionization energy. Next in line is the electron affinity, a process where a gaseous atom embraces an electron to morph into a negative ion, liberating energy in the meantime. This is followed by the transformation of these gaseous ions into a solid ionic compound, a process that sets free the lattice formation energy. By meticulously adding up every bit of these diverse energies, we arrive at the change of formation of the ionic compound. This crucial number, the enthalpy change of formation, enables us to calculate the much sought-after lattice energy. In order to simplify this, let's think about the creation of sodium chloride, commonly known as table salt. Sodium atoms undergo an ionization energy process, where they lose an electron to transform into positive ions, while chlorine atoms exhibit electron affinity by an electron to become negative ions. These ions then unite to develop a solid crystal structure of sodium chloride, a process which is accompanied by the release of energy. This energy release, known as lattice formation energy, can be quantified using the Born-Haber cycle. It's crucial to bear in mind, however, that lattice energy is not a physical magnitude we can measure in a straightforward manner. Instead, it's a theoretical concept which facilitates our comprehension of the properties of ionic compounds. To conclude, lattice energy serves as a yardstick to gauge the power of the forces that bind a crystal in unity. This measurement is derived by using the Born-Haber cycle, an indispensable process in chemistry that weaves a relationship between various physical and chemical properties. Enthalpy change of formation is a key aspect of the Born-Haber cycle, intricately linked to the calculation of lattice energy. A grasp on the concept of lattice energy empowers us to predict the characteristics of ionic compounds, including their stability, melting point, and solubility. Hence, the next time you add a hint of table salt to your meal, bear in mind that it's not just sodium and chlorine atoms that you're witnessing, rather a sophisticated symphony of forces and energies that maintain the crystal structure. In the labyrinth of chemistry, captivating principles like lattice energy make the study infinitely interesting. Here's to enlightened learning.